you ask a computer if you are friends with someone, it doesn't look at your text messages or your shared history or, the fact that you both like the same obscure bands.
Right, it doesn't actually feel a connection.
Exactly. It looks for a perfectly symmetrical, mathematically bulletproof grid. It needs an absolute definition of what a connection actually is. So today's deep dive is about the invisible absolute logic of relations. Basically, the mathematical rules that secretly govern your entire digital life.
And to really understand that invisible architecture, we are looking at a transcript from a mathematical lecture. It's specifically a Class 12 level introduction from the channel Mathematica.
Which, sounds intense.
It does, yeah. It deals with set theory. And while it might sound like purely academic, chalkboard math, you're actually looking at the fundamental building blocks of modern computer science here.
Wow, okay.
Yeah, it is the literal code that dictates how relational databases operate, how networks communicate, and how social media platforms decide who you know and what you see.
Which is wild. So the lecture starts by forcing us to look at the absolute menu of possibilities before we can even, define a single connection. They introduce two completely distinct starting points. Let's call them set S and set T.
Right, this is your raw material.
Yes. And to even begin defining a relationship between these two sets, we first have to calculate the entire universe of possible connections between them, which in mathematics is known as a Cartesian product.
Or out loud, you'd say S cross T.
S cross T, right.
And the thing about the Cartesian product is it doesn't care about rules or preferences. It is the total grid of possibilities. If you are building a database architecture before you can filter data, you need to know the absolute boundaries of that data.
Right.
The Sorth actually grounds this in a very clean mathematical example to illustrate it. Imagine set S contains just three elements, the letters A, B, and C.
Okay, simple enough.
And set T contains three numbers, 1, 2, and 3. So the Cartesian product, S cross T, maps every single possible pairing between those two distinct sets.
I found it really helpful to visualize this like looking at a restaurant menu. Imagine set S is your list of three appetizers. You've got calamari, bruschetta, and spinach dip.
Okay, making me hungry.
Right. And then set T is your list of three main courses, steak, chicken, and pasta. The Cartesian product isn't the specific meal you actually order.
Right.
It is every single possible meal combination you could theoretically put together from those two lists. It systematically pairs every appetizer with every single main course.
Exactly. It basically creates a comprehensive matrix. It starts with the letter A from set S and forces a pair with everything in set T. So you get the ordered pair A1, the pair A2, and the pair A3.
So it exhausts the first option?
Yep, once the letter A has exhausted its options, the formula just moves to B. You get B1, B2, B3, and finally C1, C2, and C3.
Which gives you 9 pairs.
Right. And in database management, specifically SQL databases, this exact concept is called a cross-join.
Oh, I've heard of that.
Yeah, if a developer accidentally runs a cross-join on two massive tables without applying a filter, it attempts to pair every single row in table A with every single row in table B, which
sounds like a disaster.
it can completely crash a server, yeah, just because of the sheer volume of resulting combinations.
Which makes sense when you look at how the source material calculates the size of this universe by multiplying the cardinalities.
It's just the math term for the number of elements in a set.
Right. By multiplying the cardinality of set S and set T, you instantly define the absolute boundaries of your data. A set of 3 and a set of 3 gives you a 9-pair universe.
And that resulting 9 represents the absolute limit of connections. You cannot have 10 pairs. You wouldn't have a pair that includes a letter or number not in the original sets. It is a closed, finite universe of potential.
But 9 pairs, 9 billion pairs in the case of a real-world database, isn't actually useful on its own. The Cartesian product is every possible connection. In reality, we don't want every connection.
No, you'd be overwhelmed.
Right. Going back to my menu analogy, what if I'm allergic to spinach dip and refuse to order any combination that includes it? We need a way to filter the universe.
And this is exactly where we arrive at the actual definition of a relation.
Okay, here we go.
In the mathematics from our source, a relation, which is often denoted by the Greek symbol rho, is a specific subset of that massive Cartesian product.
So it's just a smaller piece of the pie.
Exactly. It takes the entire universe of raw possibilities and forces it through a conditional rule. Only the pairs that survive the rule actually become part of the relation.
Let's look at the exact example of a conditional rule from the source material. We go back to our ABC and 1, 2, 3 sets, but this time we create a rule that locks in the very first element.
Right, a fixed rule.
We mandate that the first element must absolutely be A from set S, but we let the second element from set T vary.
And the mathematical notation handles this filtering beautifully. The source explains that you write the accepted ordered pair as a comma I. The A is fixed as a constant.
But the I is fluid.
Exactly. The I represents a variable that can be any element from set T.
So by applying that simple rule, our 9-item universe suddenly shrinks. Our relation subset becomes just 3 pairs, A1, A2, and A3.
Because every pair starting with B or C is filtered out.
Right. And this filtering process introduces 2 terms that are absolutely crucial here, the domain and the image.
Yes. In any defined relation, the anatomy of the surviving pairs is strictly categorized. The very first items in our accepted ordered pairs make up what is called the domain,
Okay.
and the second items in those accepted pairs make up the image. If you think about typing a query into a search engine, your search terms function like the domain. It's the initial input.
Oh, that's a good way to think about it.
Yeah, and the specific websites the algorithm pairs with your query and displays on your screen, those function as the image, the output.
Now, I wanted to trace out an example the source used because it clarifies a really tricky part of this concept. Let's say your starting set A is A, B, C, D, 4 elements.
Okay, track it.
Your starting set B is alpha, beta, gamma, 3 elements. We apply a rule, our relation, that only pairs up A with beta, B with gamma, and D with alpha.
Right.
If I'm looking closely at that, the letter C is sitting right there in the starting set A, but it didn't get paired with anything. So it logically follows that C is absolutely not part of the domain, even though it was in the starting set.
That deduction is completely correct.
Yeah.
And it's actually a point the source emphasizes heavily. The domain only cares about active participation.
Just showing up isn't enough.
Exactly. Simply existing in the starting pool means nothing to the actual relation. To be recognized as part of the domain, an element must successfully pair up with something based on the rule. Because C didn't pair with alpha, beta, or gamma, it's essentially a mathematical wallflower.
It's just ignored by the system entirely.
Ignored entirely. Yep.
And the image works under the exact same ruthless logic. The source uses another set B containing elements A1, B1, C1, and D1. If the relation only ends up utilizing B1 and C1 as the second halves of the pairs, then only B1 and C1 are in the image.
Right, the unused elements are just completely discarded from the relationship.
So far, we have been connecting 2 completely different sets, the letters to the numbers, the appetizers to the main courses. But the architecture shifts significantly when a set attempts to have a relationship with itself.
Yes. This is a big pivot. This moves us from a binary relation between 2 different sets to a binary relation defined on a single set.
So S cross S.
Mathematically, yes.
Okay.
The Cartesian product goes from S cross T to S cross S. Both the domain and the image pull from the exact same pool of elements.
It's like an internal corporate networking event. Everyone in the room is wearing a badge from the exact same company. That is your single set. But just because they work for the same company doesn't mean everyone talks to everyone else.
Right, that would be chaos.
Yeah, they form specific pairs based on an arbitrary rule. Maybe they only talk if they work in the same department, or I don't know, if they both happen to play tennis. The rule is what creates the relation within that single uniform set.
The source material provides a highly structured mathematical example to demonstrate this introspective relation. They use the set of all integers, denoted as Z.
So Z cross Z.
Exactly. The Cartesian product becomes Z cross Z, which is the infinite universe of all possible integer pairs.
But the relation, the rule for this particular networking event is based on addition. The rule demands that the 2 elements, when added together, so X plus Y, must equal an even number.
Yes.
If they don't add up to an even number, the pair is rejected.
And applying that logic to the infinite set of integers creates a really fascinating filter.
Let's test a few. If we take the integer 1 and the integer 2, 1 plus 2 is 3. 3 is an odd number.
So that pair is rejected. It does not exist in the relation.
But if we take the pair 1 and 3, 1 plus 3 is 4. 4 is an even number. So that pair successfully enters the relation.
And what's particularly important here is self-pairing.
Oh, right.
Can the integer 2 pair with the integer 2? Yes. 2 plus 2 is 4, which is even. So the pair 2, comma 2 is absolutely valid.
That makes sense.
By running this rule, you filter the infinite grid of integer pairs down to only the ones that satisfy the even number condition. You create what mathematicians call a proper subset.
Even though it's still an infinite amount of pairs.
Right. It is still infinite, but it is a strictly filtered infinity.
So once mathematicians established that a single set could relate to itself, they stepped back and analyzed the patterns. They realized that these internal self-relations don't just happen randomly. They actually tend to conform to three distinct, highly logical frameworks.
Yeah. And the source spends a significant portion of the lecture outlining these frameworks. They are reflexive, symmetric, and transitive relations.
And understanding these three behavioral rules is basically the key to understanding how complex systems map data.
It really is.
So the first framework is reflexive. The core definition here is that for every single element in the set, it absolutely must pair with itself.
Yes. If your set has elements A, G, and C, your relation subset must contain the pair AA, the pair BB, and the pair CC.
It is an uncompromising mandate of total participation. The source illustrates this strictness really clearly. If a set contains four elements, A, B, C, and D, and you successfully map A, B, B, and CC, but D somehow fails to pair with D, the entire relation fails the test.
It just completely breaks.
Yeah, it is stripped of its reflexive status. It requires absolute completeness.
And in data logic, this ensures every single node in a network can reference its own baseline state without throwing an error.
Wow, okay. The second framework is symmetric. This rule states that if a pair AB exists in the relation, then the reverse pair, BA, must also explicitly exist.
If A points to B, B must point back to A.
The source grounds this in a really clever analogy using the famous cricketer Virat Kohli.
It's such an excellent way to conceptualize directional logic.
Imagine a relation defined by the concept of knowing someone. You know the listener, know of the famous cricketer Virat Kohli. In our mathematical pairing, the pair you, Kohli exists, but Virat Kohli does not know you. The pair Kohli, you does not exist. Therefore, that relationship is not symmetric. It is a strictly one-way connection.
Exactly. If the relation were truly symmetric, your knowledge of him would mathematically guarantee his knowledge of you? Because it doesn't. It fails the symmetry test. Every single AD pair must have a matching BA pair to act as a counterbalance.
Think about how this exact mathematical rule built the modern internet.
Oh, absolutely.
Like Facebook was built entirely on a symmetric relation. You cannot be friends with someone unless they explicitly confirm they are friends with you. AB forces BA.
Right.
But Twitter was built on an asymmetric relation. You can follow someone, but they are not required to follow you back. That single mathematical difference in how the database treats a connection completely changed how information flows through society.
That is the exact power of defining the relation. It dictates the fundamental architecture of the network. Which brings us to the third framework, which is transitive.
Transitive, okay.
This dictates how data chains together. The transitive rule says if element 1 relates to element 2 and element 2 relates to element 4, does element 1 relate to element 4?
Okay, so a chain.
Right. In letters, if the pair AB exists and the pair BC exists, then the pair AC must exist for the relation to be considered transitive.
A knows B, B knows C, therefore A knows C. It's the logic behind the people you may know algorithm.
Exactly.
But wait, looking at transitivity, if A relates to C and C relates back to A, the rule of chains would mean A has to relate to itself. So the transitive rule can actually force an element to be reflexive just to keep the math from breaking.
It absolutely can. And that is a brilliant deduction that the source explores. It follows the exact same logical chain, just with a looping cast of characters.
Okay.
If you have the pair AC as your first link and the pair CA as your second link, the transitive rule demands that the outer elements of that chain connect.
Let me think about that.
The first element of link 1 is A. The last element of link 2 is A. Therefore, the pair A must exist in the subset. If AA isn't there, the transitive chain is broken and the relation fails the test.
Wow, so it literally forces a reflexive-looking pair into existence purely to satisfy the transitive law.
It does. And there's another facet of transitivity the source covers that feels entirely counterintuitive at first glance. It involves a concept mathematicians call vacuously true.
Vacuously true. That sounds like a polite way to tell someone their argument is just totally empty.
In a way, it kind of is. It's this really elegant mathematical loophole designed to prevent systemic errors. Imagine you have a relation with only two pairs, A, B, and C, D.
Okay.
There is no overlapping middleman. B doesn't connect to C. There's no chain to test.
So does it fail the transitive test because it can't form a chain?
No, it actually passes.
Wait, really?
Yeah. Because there is no chain to test, the rule cannot be explicitly broken. In mathematical logic, if a rule isn't explicitly broken, it is considered to have passed. It is basically innocent until proven guilty. A set with just A, B, and CD is technically vacuously transitive.
Because it didn't fail, it wins by default. But why do computers or mathematicians even need a loophole like that? Why not just say it's undefined?
Because computers hate undefined states. If an algorithm is sweeping billions of data points looking for transitive relationships, and it hits an isolated pair like AB, it needs a definitive yes or no to keep running.
Otherwise, just get stuck.
Exactly. By defaulting to vacuously true, the algorithm can safely categorize that isolated data without throwing a critical error loop. It allows the system to remain mathematically sound even when the data is super sparse.
That makes a lot of sense. So, if we pull all of this together, we started by calculating the absolute boundaries of our data with the Cartesian product. We then learn how to filter that massive universe down by applying specific rules, creating a relation where the active inputs form the domain and the active outputs form the image.
Right.
Finally, we looked inward, exploring the strict behavioral rules that govern how a set relates to itself: reflexive, symmetric, and transitive.
It really is a remarkable journey from abstract Class 12 mathematics directly into the engine room of modern technology. I mean, every time a database cross-references two tables, every time an algorithm maps a network of users, it relies on these exact logical tests.
Which leaves us with one final fascinating concept to consider. The source material actually ended by teasing a future lecture on something called congruence modulo n and equivalence classes. But the breadcrumb they leave behind is pretty profound. Consider this. What happens if a specific relation perfectly passes all three of those tests at the exact same time?
A system that is simultaneously reflexive, symmetric, and transitive.
Exactly. In mathematics, when a relation pulls off that perfect hat trick, it is crowned an equivalence relation. And an equivalence relation is basically the holy grail for a computer algorithm.
Oh, for sure.
When a relation possesses all three of those properties, it allows a computer to take a massive, chaotic universe of data and cleanly slice it into distinct, non-overlapping categories, where everything inside a given category is fundamentally equal.
And the computing power saved by that logic is staggering. If a database knows A equals B and B equals C, it doesn't need to waste valuable storage space saving the fact that A equals C. It can mathematically deduce it on the fly, saving millions of operations.
It creates perfect order out of total chaos. So the next time you look at your digital footprint, when a streaming service predicts exactly what movie you want to watch, or your photo app flawlessly categorizes hundreds of pictures of your dog.
Which is always impressive.
It really is. Ask yourself how the algorithm decided that two completely different pieces of data belong in the exact same class. We tend to think of our connections as organic, messy, and entirely subjective. But behind the screen, the system is always searching for that perfect equivalence relation, constantly working to force our messy human world into perfectly symmetrical transitive boxes.